The immune system of the plant is at least 50% the microbes in the soil.
Today we jump onto a Zoom call with Judy Fitzpatrick, co-founder of microBIOMETER. I'm Aaron Moskowitz, and this is episode 81 of the Get in My Garden podcast. The first few minutes of this episode, Judy shares her backstory, her history in medical diagnostics, and then about co-founding soil microbial biomass testing company microBIOMETER. Judy shares about the distinctions of different available types of soil testing on the market, which is very enlightening. She explains the process by which scientists breed and study bacteria in the lab setting to create strains with a specific purpose for the garden or for medicine. Then we dive more into microbiology, how bacteria breed, how their DNA gets shared around as they adapt to their environment, and so much more. We learn how to understand the ratio of different fungi and bacteria, how to use this information to gain an ideal soil structure, and how it all works at the microbial level. Thanks for listening to the Get in My Garden podcast. Please subscribe wherever you listen from, and if you want to support the show, please take a moment to leave a positive review on iTunes and elsewhere. It really helps with the rankings. Follow on Instagram at Get in My Garden, and check back early spring for a new blog format on the website, getinmygarden.com, where you can also sign up for the newsletter blast.
I entered the field of microbiology and going back to graduate school at Mount Sinai Medical School. So I was actually thinking I would enter the vaccine field. So I was very interested in immunology. But by the time I had graduated in 1981, the vaccine industry in the United States, interestingly enough, had evaporated because the lawsuits had gotten so much that vaccine manufacturers left. So I went into worked on developing one of the first immunoassays for pregnancy. The division of the company that I was with was doing radioactive testing at that time, and they decided to close that down. So I took that opportunity to leave, and I started a company called CRX, started teaching at a local college. And they asked me to apply for a National Science Foundation grant to set up a quality assurance program. So training people in, following quality assurance guidelines. In the industry that I was in, which is testing and drug development, I worked with a lot of the drug developing companies who want tests to go with their drugs. 50% of the people they hired don't make it through a year because it's very hard to follow quality control very strictly. So I set that program up, and when I was about a year through it, I was really missing research, and I was running the quality assurance program, and I met my co-founder, James Sotillo, who was treating all of New York City in a sustainable, regenerative fashion. So he was treating all of the New York City properties, and he managed all of them at that time, Central Park, all of them organically. And he gave this talk on it, and then he said, the one thing we really need is a test for microbial biomass, because only the microbes can really tell us that we're in a healthy environment. So I went up to him afterwards and I said, I've developed a medical diagnostic test. This could be rather interesting. I puttered around with it and pulled him up. He always liked to say, the crazy lady called me up 6 months later and said, would you like to come see our test? Meanwhile, I'd gotten permission from National Science Foundation because they said this would be a good quality control test for soil. And I started working with students on Saturdays doing that. So the first test was just looking at turbidity, because isolate enough microbes from soil that the solution became, and sometimes so dark, even if it was in a tube a half-inch thick, you couldn't see through it. That many microbes in a half cc of soil. So unfortunately, James Sotillo, at the age of 51, died suddenly 18 months ago.
I'm so sorry. Wow.
Yes, yes, it was a great loss. I really enjoyed working with him. But the test went through a number of iterations. Then we said, okay, people don't really like to rely on a visual evaluation. They're not comfortable with it, doing something along that line. So we changed to reading it in a little colorimeter that we had.
I saw that, yeah.
The colorimeter was setting it up was a little intense. It was a program that went with it. And people only test 2 or 3 times a year, so they don't remember a program like that. They wanted something really quick.
Okay.
So I had to redesign the test to improve the extraction method and get more microbes extracted in the extraction fluid. And then I made a visual test. And we had a little screen, a red screen you put over it, and you could read it and compare it to the grayscale that now encircles where we put the sample.
Mm-hmm.
And then Brady started working on getting that to read with a cell phone. Basically, half the test is the test that I developed. That's the actual assay. But what really allows it to be used in the, on site and makes it so easy is the app that he has so skillfully developed.
I agree. Yeah, I was looking at the app. It's amazing what you've got there and how it can be used. And as far as the focus of understanding the soil that it can give you, can you explain a little bit what differentiates it, comparing it to other existing tests out there?
There's a test for soil respiration, and you can buy a kit for that from Solvita.
Uh-huh.
And for that test, really, to a large extent, it requires a lab because first you have to get the soil and you have to dry it. And after you dry it, you need to weigh out 20 grams of soil and put it in a cup that they provide and add an aliquot of water. So they tell me how much water to add. And then you put it in a jar, and they have a gel on a stick that you put in there. So it's a pH indicator.
Uh-huh.
And you stick that in, and you put it in a dark space for 24 hours. And then you read the color on the gel. It's very hard to read the color on the gel unless you have their instrument, which sells for about $1,800. The difference between respiration and soil microbial biomass is that respiration is actually telling you the metabolic rate or how hard the microbes are working. So if you have 10 people who are working out, they're making a lot more carbon dioxide than you and I are sitting here in a chair on a Saturday afternoon.
Yes. Well, I'm actually at a standing desk, so I'm producing more.
Okay, good for you. So in the rest of the world, this test is used only to indicate whether the microbes are under stress. So what we do is we look at what is the carbon dioxide output, which is calculated from their instrument, from their test, and you divide it by the microbial biomass.
Okay.
If they're working really hard, that tells you that there's something wrong. So they're not saving carbon to the soil. They're putting carbon dioxide back into the air.
I see, yeah.
So you're not sequestering carbon. And there are things that make that light. So like if you're testing soil with low pH, it's no secret that those microbes work harder than those that are at a neutral pH.
Mm-hmm.
So they imply that you know how many microbes are there because of this, but in actuality, you don't. The other issue is that we've done experiments, and what we have seen, it's led to problems with other tests that we'll talk about, is that the microbes that die when you dry the soil are the microbes that are most active at the time that you collected the soil.
Mm-hmm.
When we treat cancer, what we do is we kill active cells, because cells that are actively dividing, which is what microbes do when they grow, they just divide.
Uh-huh.
They don't get one cell gets really big like ours can. So what you're seeing is you're not taking a real look at the soil as it exists in the garden. Some soils, when you dry them, the microbial biomass goes down like 20%. And in some of them, when you dry them, it'll go down 80%.
Amazing.
And when you re-wet them, they don't always come back to where they were. Sometimes they do, sometimes they don't. You don't know what's going to happen.
So at this point, people are paying money. They're sending off their soil, paying money to get it tested. They're not even getting a full picture of what they've got.
They're not getting a picture of actually the microbes that they have. Now, there are cases in which where you should be using respiration. And I can just quickly tell you one that I know of because I've talked to the guy who does it. There's there's companies out there that sell you microbes that you can put in the soil that will eat oil and get rid of your oil spill. Now, you really want to know that those microbes are working hard.
That makes sense.
So they actually use microbial respiration to measure that.
Do you, off the top of your head, know what they're putting in? So is it a fungus or you're talking about a bacteria?
There are bacteria that are known. They spray them on oil spills in the ocean and things like that. So, and there are microbes that have been bred to eat other toxins. Mm-hmm. So it's a very good idea to get rid of a toxin by using a microbe that can actually metabolize it into something that is non-toxic.
I see what you're saying. And as far as like remediation goes, I mean, you're potentially producing a lot of carbon, but then after it's balanced, you can go back in there and start building the soil with proper agriculture and potentially sequester it again. Is that right?
Right. And I'm not sure like on how big a scale all of this is done, but obviously when they're treating oil spills and spraying these microbes on, that's a huge job.
Oh, yeah. Well, on that subject, I mean, it's completely fascinating, and we face many ecological problems, which we will have to use technology to fix. Well, I mean, that's my opinion, I guess. But as far as the microbes and how they're bred and how they do adapt, what can you tell the listeners about the adaptability of the microbes in their soil and their ecosystem?
That's a fascinating subject. And it's very broad. So I will only probably nibble at the edges of it. But what they do is they'll take a whole bunch of soil microbes. So the first thing, like let's say I wanted to develop an assay that would see if I could metabolize oil. Mm-hmm. What I would do is put it down on a plate in the lab. So I put it on a nutrient. And I would make that nutrient probably pretty poor in everything but the oil. Uh-huh. And I would see what microbes survived. So I may only get a couple of microbes to survive. But then I would try to build those 2 or 3 that survived up. And I would continue plating them out on plates that had increasing amounts of only oil. And I would be breeding then for microbes that could adapt to just living on oil.
I love it.
There's a man in famous Russian, whose name doesn't come to me right this minute, who domesticated foxes in 20 generations. Uh-huh. He just kept selecting for the foxes that were the most wanted and were comfortable dealing with humans. It's not so different what happens with microbes as with animals.
I'm guessing it happens much more quickly.
In microbes, yes, you just hit on that, okay? And I can tell you why that happens. If your DNA and my DNA are as different as my DNA is from a female gorilla. Okay. So that's because you're male and I'm female. Mm-hmm. And the difference between both of us and our male and female counterparts is less than 1%. But the difference between one E. coli and another E. coli is 20% DNA difference.
Wow.
That's like the difference between us and a cow being the same species.
Amazing.
That's because these guys basically have a lot of sex. People, don't usually think of them as sexual, but they transfer DNA back and forth between one another. And when they die, a lot of times DNA just falls out of them, okay? And another bug will just pick it up and it'll integrate it. This happens all the time. So these microbes are continually changing all the time.
And they're changing based on the DNA of unrelated species too, right?
Yes, you're absolutely right. So, they can pick up DNA from other groups too.
So how does that exactly work? I mean, it's obviously, it might take like a whole day to explain it, or it may take 5 minutes if there's a explanation for people who are just totally fascinated by that so that they could learn a little bit more.
Well, one of the big ways it happens is bacteria have a chromosome. And in addition to a chromosome, they often carry small circular pieces of DNA. Their DNA is circular too. Mm-hmm. Called plasmids. And the plasmids carry, up to like 10, maybe 20 genes, but usually it's a smaller amount of genes. And these plasmids have the ability to form extensions of the cell membrane and go to another bacteria, penetrate it, and insert that plasmid into that other bacteria.
Wow.
And then that bacteria can be making copies of something all the time.
But it's making decisions based on what it needs, right?
So you can load it up with plasmids, and it can, on whatever it wants, it can just make more and more plasmids. These plasmids can insert themselves into the actual DNA molecule of the bacteria, or they can stay as plasmids. So we make some drugs now that way by increasing plasmids, like insulin is made that way. We have whole tanks and tanks of bacteria filled with plasmids that allow them to synthesize insulin.
Gotcha.
And that way we can make human insulin in a bacteria.
With the microbiometer, it will tell you what ratios of fungus and bacteria exist in the soil. But what do you do with that information?
Microbiometer tells you two things. One, it tells you how many microbes you have. It does not detect dead microbes. We've tested by staining. We know it doesn't. So it detects most of your microbes most of the time. They're not active. They're only active when it's needed. They can hibernate, and then it's like an orchestra. Not all the instruments are playing at the same time.
Uh-huh. And I heard they can stay dormant for years and years and years.
Thousands of years. So what do those microbes in general do for you? Well, the microbe stays in the soil because it sticks itself to a soil particle, and it sticks very tightly. So when you put fertilizer into the soil and you feed the microbe, instead of just hoping it gets to the plant, it's going to stay in the soil for you. It's stored in those microbes. Mm-hmm. And the glue that the microbes, both the bacteria and the fungi, extrude in order to stick them there is what gives soil its structure. So it kind of holds together rather than being like a powder. And that structure, when you have a good structure, allows you to hold 50% more water. That's not being, sloggy with muddy and stuff like that. The texture actually just holds more water for you. And while you have that texture, it also can hold more air. So two things that your plants and your microbes need in the soil is water and air. And within a couple of years of doing cover cropping, lots of people see tremendous increase in their soil structure. And the other thing they do is they provide nutrients. So there are rhizobia, that actually invade the plant. And in that colonization process, they produce nitrogen right in the plant for the plant.
Are those the bacteria that relate within the roots themselves?
Yes.
Okay, got it.
Okay, those are rhizobia, but there are free living rhizobia in the soil too. and they can be turned onto the plant to produce nitrogen. And they only multiply when they're told to by the plant.
Mm-hmm.
And when you're doing a chemical test, the chemical tests that are done now by labs, those tests are all over 100 years old.
That's amazing.
And they tell you what is chemically available. They don't tell you that the fungi can mine from the soil, because most of the phosphate in the soil isn't free or available when you just measure phosphate.
Mm-hmm. So it's stuck within the rock, right?
It's within rock. Okay. So you're not measuring that, and most soils have more phosphate than they'll ever need at this point.
That's something, because, so much of commercial agriculture is based on adding it in, and we're running out, I heard, in about 50 years.
Yeah. And it's there. If you get a good fungal population, an adequate fungal population for the kind of agriculture you're doing and the kind of soil you have, then you don't need it. And you may not need nitrogen either.
People so if they aren't getting an accurate reading because they're using archaic methods and they're adding that in, they're potentially really damaging and setting back the recovery of their soil. Is that right?
Absolutely. And what is the stimulus for a plant to feed the microbes in the soil? Because, of course, that is what feeds the microbes in the soil, right?
Mm-hmm.
They need the carbon from plant or dead plant material.
Uh-huh.
What causes them to put 30% of their energy into the soil for the microbes is they need nitrogen or phosphorus, etc. So once you give it there in liquid form or in mineral fertilizer, they stop feeding the microbes.
Mm-hmm.
When I go to fields that are heavy, anybody goes to fields that are getting heavy mineralization like they're getting, the microbes never come above 100. They're killing their soil, and they have no structure either.
Are they preventing the plant from being able to do what it naturally does? And are they ruining the immune system of the plant?
They are ruining the immune system of the plant. The immune system of the plant is at least 50% the microbes in the soil.
So if they've gone in that direction, what is the length of time it takes to remedy it?
Well, I think it depends on how intensive the remediation is.
Mm-hmm.
And how conducive climate conditions, et cetera, are to affecting that. In a dry climate, obviously, it would be more difficult than in a temperate climate where you had, more growing time.
Mm-hmm.
And more water, enough water to do things and stuff like that. One of the things that stumped me at first because I've been working now in this since 2013, was these guys need to be scientists, because it's the bugs, it's the plant you have, it's the soil you have, it's the climate you have. And nobody has exactly what you have.
Yeah, I totally know what you mean, because I'm dealing with unbelievably terrible soil conditions in New Mexico and really drastic weather changes and lack of water. So there you go.
So you need your AMF.
That's right.
Your muscular mycorrhizal fungi.
Yeah, I read that in Jeff's book, and I saw you actually talked a lot with him about that. And it's the most amazing thing. I feel like that might be the future. If there's more research into this, I'm sure there's, a lot more about how much research has been done, but its ability to improve soil salinity problems, any problem, or, even the plant's ability to function in a drought condition or something.
Well, it's very effective in the drought condition. I'm giving a talk through acres on the immune system, and we will talk more about AMF. But one of the things that's very interesting is when the plant is colonized by AMF, it causes, during dry conditions, it stimulates the plant to build up sugars in the root. And the root actually swells, the cells become so thick with sugars. And what that happens is it raises the osmotic pressure, okay?
Mm-hmm.
So water flows into the plant from the soil, okay? So it actually stimulates the plant and you can see really big differences. And I have pictures of that in my talk on immune system. You can see pictures of that. Maybe the root is 2 or 3 times as large, extended for the increased osmotic pressure that is stimulated by the AMF. And of course, the AMF can increase the surface area of the root up to 1,000-fold.
Wow.
And that means, okay, since the AMF are much smaller than even tiny root hairs, it allows the plant access to 1,000-fold more area of the soil for bringing in water and nitrogen and phosphorus. So nitrogen is also scavenged by fungi, and I would be surprised if, other minerals weren't also scavenged. Mm-hmm. Some of this research is still really ongoing.
It seems like it's unlimited what they can potentially get from the soil. And it seems like the microbes, having done this for millions or billions of years, they're set up to know exactly what to signal for.
If you think about this, what's really, really interesting is many of the microbes that we see in the soil now have been around for almost 4 billion years. There are no other plants or animals or anything that is a species that lasts that long. That really explains to you how nimble these bacteria are in how they can mutate and change and adapt to so many different conditions that they've been able to survive for this long.
No kidding. Well, one thing that I was curious about, and I know this is also something that's still being researched, but the idea that if you have a non-native plant, which has no history of working in that ecology of that area that you're replanting it in, and adding to that, if you get a plant through a conventional greenhouse that's using conventional fertilizer, you put it in your backyard. I've heard from different people estimations on how it makes it so that maybe that entire area around that plant, it doesn't adapt, and it also doesn't foster the same insect life going up the soil food web that will end up feeding the birds. This I got from Douglas Tallamy, he's the ecologist who his mission is to help transform the world through people's backyards, so turning them into wildlife corridors and eliminating as many turfs as possible and reintroducing keystone species and native plants.
Yes. Okay. Yes, I listened to that. So you're absolutely correct. And so to bring that back to AMF, I'd like to kind of address that. People are selling AMF strains. And so we said there was a 20% difference in a microbe's DNA, and they can change it pretty quickly. And a new strain can become very dominant very quickly.
So it sounds promising, actually, as far as the existing landscaping paradigms, that's something that might benefit those disconnects in introducing non-native plants.
Well, the issue is when people put in AMF, now people are recommending that you just try to build up the AMF that are adapted to your conditions. Mm-hmm. Okay. Some people are having luck with the AMF. If you get a seed actually has microbes on it.
Right.
And the seed really needs the microbes that are on it, and often there are AMF on it. And so you shouldn't be washing them or treating them with Clorox or doing anything like that. These are the AMFs that took care of its mother. So just as human babies are inoculated by their mother's bacteria, basically fecal bacteria during birth, plants get a dose of their mother's microbial growth, and they need that. Those are the ones that will help them grow. We know that babies that are born by cesarean have much higher levels of immune disorders than babies that are born naturally.
Yes, that's something.
Yeah, so it tells you like the microbes that are natural to your area have a much better chance of growing.
Thanks for listening to the Get in My Garden podcast. For more information on microbiometer or to see more of Judy's work, visit microbiometer.com. Next episode will be a continuation of this great soil and microbe discussion with Judy Fitzpatrick, and then we'll have an episode with Jordan Mara of Mind and Soil, sharing about the mental health benefits of gardening. If you want to support this show, please take a moment to leave a positive review on iTunes or elsewhere. It really helps with rankings, and subscribe wherever you listen from to be notified of new shows. You can follow the podcast on Instagram at GetInMyGarden, and check back early spring for a new blog format on the website, getinmygarden.com, where you can also sign up for the newsletter blast.